Well, hello everyone, and welcome back to Adrian's Digital Basement. We're back on the Plexus P20. This machine is a very rare dual processor, multi-user Unix workstation from around 1985, and I've been on quite a journey trying to get this machine working. This is part 5 in the series. If you haven't seen the previous parts, I really recommend you go start from the beginning if you haven't seen any of them, or at least catch up on the ones you missed, because as usual, this part 5 is going to be a continuation where I left off in the last part. To give a quick recap, in part 1, I took this machine apart and we saw the glorious huge motherboard in here, and we took out the hard drive and I imaged it. So I got a good image of that old hard drive, which if you think about it is what, like 40 years old at this point, and yet it still works. In part 2, I had to service the power supplies because there were refas in there, and plus there were some other faults. So I got those serviced and I actually powered up the computer for the first time. And after figuring out the pinout of the serial ports, I was able to actually get some action on the boot ROM. Part 3, I hooked up the hard drive, the original hard drive, back to the system, powered it on, and the computer worked. It freaking booted up into Unix. I couldn't believe what I was seeing, and I thought that was going to be the end and just be me playing around with the system, but it quickly went wrong and the computer failed. There were 2 faults that developed. One of them was that the reset circuit that's inside the power supply had gone bad and it was just keeping the computer in reset, so the system would never actually boot up. Once I bypassed that, it turned out there was a critical failure that the diagnostic ROM was detecting, and it would prevent the computer from booting whatsoever. And then that brought us to part 4. And in that part, I talk a lot about the architecture of the system and the work that's been going on in the background on Discord on both the hard drive, recovering data from that, and the design of the motherboard and the reverse engineering of the ROMs. In order to fix that critical error in part 3, I had to know what was wrong with the diagnostics, what it was stopping on. And the great people on the Discord channel that David set up, that's David at Usagi Electric set up on his Discord server, they were able to get to the bottom of exactly what was wrong with that error code, what it was stopping. And it turned out that it was actually a flip-flop chip that was bad. It had gone bad, and it was right in the area of the battery leakage that had happened from the leaky battery. So probably was related to that, but it's amazing it worked for a little while and then it died. That main flip-flop generated a signal that was necessary to allow this processor here, which is the one that boots up the system, to talk to the main memory. And that signal was bad, which meant that the processor could never communicate with the RAM. So once I swapped out that chip, that fixed that problem. But then we ended up with another issue. The diagnostics said there was a failure in the clock circuit, which is almost certainly the clock chip right here, which is the same clock chip that's used on the IBM PC AT5170. And it also said there was a multibus error, multibus being the expansion chassis on the front of the system. I fiddled around with the motherboard for a bit to see if I could get rid of that error, but even power cycling and checking the connections and stuff like that, it didn't go away. It happens every single time. So in this video, I hope to get to the bottom of both of these errors and get this system finally booted back into Unix once and for all. And hopefully it stays working this time and doesn't just die after 20 minutes. So without further ado, let's get right to it. All right, we have the patented talking hand over the motherboard, and that's because this thing is so big it really doesn't fit on the bench, so I gotta do a lot of the work over here, which is why there's a little oscilloscope sitting here and the multimeter. All right, so I want to address a couple things. A few people pointed out that I probably needed to have the multibus expansion installed on the front in order for the system to boot without an error, and that this board needed to be installed. This board is only required if you're using a second power supply. There's a connector right here that can go to the power supply, and that feeds the pins that go to the back plane that supply power to the other cards. So you can either connect the power supply here, or you can connect the power supply directly to the back plane, because it also has a power supply connector. Now, when you look at the backplane, because you can see the traces clear as day, the power supply connector on the backplane also just goes to these same pins right here. They don't feed the motherboard. The motherboard has no idea that power supply is there or not there. It just feeds this card. Or obviously, if you have any other multibus cards installed, it will feed those with the requisite power. I'm assuming normally you would plug the power supply into this if you're using this board, just because you're not going to put any stress on the traces that are on that multi-plane backplane. The power that goes into this connector will just be turned into heat through all these resistors. But obviously, if you're not going to use multi-bus, you don't even need this, and you just unplug the power supply, which is what I've done, and that simplifies that whole process. Now back to this card cage on the front here. The reason why it's actually on the system right now is because I just wanted to validate that it was not required for the system to boot properly. But I know this actually wasn't. So even though you see terminating resistors right there, I had this thing booted up into Unix without this card installed. So in part 3, this thing was never in the machine, and it was definitely running Unix without any kind of issue. And then we had the failure of the chip on the board. My assumption is that this system came in 2 configurations. One didn't have any of this multibus stuff. This was missing, and so was that second power supply. So the motherboard obviously has to work properly without these installed because, well, that is the P15 configuration. This is the P20, which means it came with this, and that extra power supply. And if you're going to run everything together, then you just need to make sure the resistor board is in there so the power supply doesn't have any regulation issues with this all installed. Now back to the issues that this thing is having. We have those 2 errors. I think the first thing I need to do right now is power this thing back up because it's been a little bit of time since I last worked on it. And let's make sure that it still has that same failure. All right, I have the key replacement, the screwdriver. It's like I stole the car here or something. Let's turn the computer on. All right, is it coming out of reset? Yes, it is. There it is. So all the usual noises are happening. Self-test revision 3.3. I'm assuming this thing will fail in exactly the same way. Now back in part 3, when we had the problem where it couldn't talk to the RAM, this self-test would fail very quickly, and it would fail with that 4F02, that was unable to talk to the RAM. But now there it is, takes longer because I think these tests run sequentially, and it gets to the multibus and it says it has a failure, and then it gets to the clock and then it says a failure. I think it's running a couple more tests there. And yeah, it told us the config value or config info is invalid. What that's talking about is just like on a PC, when you fire it up, when there's no battery, you'll get like a CMOS checksum failure. You go into the CMOS, you configure it, save it, then everything is good. It's telling us that the config info is invalid. Well, of course it's invalid because the clock chip has no battery on it. And those Motorola MC1468818, that's the chip that's in there, when they're uninitialized because there's no battery on there, that when you power them up, they just have a bunch of random garbage in there, and it needs to be configured by the OS or the ROM or whatever. And then with a battery, obviously that gets saved. Or usually with those chips, they stay running while the computer is powered up. So as long as you don't turn it off, you're actually going to have a valid configuration. It's just once you shut it off, it will lose those settings. Anyhow, I have validated the system is broken in exactly the same way it was in part 4, which is good. I don't like things when they spontaneously fix themselves. And this actually brings me to the next awesome thing that the folks on Discord figured out about this system. They have been consistently working on reverse engineering the ROM, and they have figured out that there are a bunch of commands that you can do to do things while you're in this ROM, even in the halted state that we're in right now. So let me demonstrate some of the stuff that they have figured out. One of the things that were figured out is that if you hit Shift and 1, which is the exclamation point, what that does is it exits out of the halt state. And you can see we're at the Plexus primary boot or version 1.2 prompt, which is exactly where we were in part 3 before the system failed. Now, if I hit enter, it should load the Unix kernel and start booting the OS. And yes, that's exactly what it's doing. It should print how much RAM it has available and then load the system. And right here is where things go wrong. The system is actually halted. It's frozen right now. So we have a Unix 1.2 in the real and available memory. And if I recall from part 3, what happens next is it asks us to set the clock. And I have a feeling it's probably trying to talk to the clock right now, which I don't think is working because it says clock failed. And that's probably why the system is hanging up right now. So I'm going to use the old screwdriver here, and let's reboot the computer by switching it into reset. So there we go, and out of reset. Okay, that's going to boot back up. That's my AT Tiny in there that's allowing that to happen. Now, here's another cool thing that they figured out. I have this terminal profile for PuTTY here configured to send Control H when you hit the backspace key. And that was because when it was booted into Unix in part 3, that's what I found it needed for me to have the proper backspace. But if you change it to this Control H or decibel 127, and I press the delete key, it drops us into a menu called DMA. Now, DMA, as I mentioned in part 4, the last part, that is the name of the processor that's running the diagnostics right now, the other one being job. And it seems that there are a whole bunch of commands in here that you can do additional diagnostics, which we don't fully understand yet. I did a bunch of button mashing in here. I was playing around with this earlier, and I found if you hit the T key, it runs all the tests, but it's gonna do it in a way that is gonna be verbose. So it's actually gonna give us info about what's running, as opposed to when you first power on the machine, it just says nothing until you get an actual error. So you can see it tested the ROMs, the static RAM, the SIOs, it tested the RAM, which was failing before, right? That was what we were stuck on in part 3. It's now testing the job processor, the map, the mapper, the SCSI. Here's testing the multibus. Let's see what happens. Multibus passed, but now it's testing the clock calendar. And yeah, check it out, config checksum error 85. So that's the error of the config checksum. I guess that's, I don't know, whatever, a specific error code. And then we get that final warning. But all of the tests pass except the clock calendar. So strangely, the multibus test passed. But let's talk about what we're seeing here with this clock output. So on this system, it appears that the clock chip is assigned to D0 and then 0000. That's where the clock chip resides in memory. The 68000 is a memory mapped IO system. It doesn't have separate IO address space like Intel systems. So every type of peripheral on this system has to be mapped into the main memory space. And it's a 16 megabyte memory space. So you have to carve out little chunks for the various systems, SCSI and the clock and whatever, all the different stuff. Well, this is where the clock chip is. And the DMA processor is obviously trying to read from the clock chip, which is incidentally only an 8-bit chip. And that's why it's skipping every other address here, because of course this is a 16-bit processor. Well, it's a 32-bit processor really, but it's reading everything in 16-bit chunks. But since it's an only 8-bit chip, it's only gonna happen on every other memory location. So it was trying to read out all the various values inside the clock chip, which is gonna include like the time and a little bit of NVRAM that's in there. And it received a 1, but it was expecting a 2, and it received a 2 and it got a 4, and so on and so forth. And you can like scroll through all this stuff here, and it got back nothing of what it expected. Obviously, there are some values in here that are going to be just garbage, and that's obviously because the configuration is lost because it's just garbage inside the chip. But a bunch of these things will have consistent values because they're status bits and stuff like that, and it's not getting anything back that it expects. Every single address gets back the wrong thing. Well, that pretty much tells us one thing. That tells us either the clock chip is bad or the logic that connects the clock chip to the CPU is bad because there's gonna be some buffers and stuff like that, or potentially the select logic for the clock chip is bad as well, because just like any other peripheral, you need to turn it on and tell it, hey, I'm talking to you, respond back, please. So it's gotta be one of those things that is the problem. Now, when it comes to the multibus error that we're seeing up here, this multibus failure, notice that it comes before the clock test. Well, I asked the folks on Discord to look at the flow of the diagnostic, and I wanted to know, does this ROM check the contents of the clock chip, of the NVRAM in the clock chip? That's the configuration data. Does it check it for multibus configuration? Like if you have a card in there that's a multibus card, does it go to the clock chip and say, hey, load the config, and maybe in there's some values for whether you have multibus cards? And that causes this multibus test to actually fail because it's reading back garbage that actually says that there's a multibus card, which of course there isn't because there's no cards in there, and that's gonna fail. And the reason why I think this is exactly what's happening is if we go back all the way to part 2 and we look at what happened with this machine on one of the times I turned it on, it got a multibus error. But it didn't get the clock failure, but it got a multibus error and then it said config value invalid, like the checksum thing was wrong with the config value. Well, on the next reboot, the multibus error went away. I think what happens is the system automatically, once it detects invalid configuration in the NVRAM, reconfigures it, probably sets it up to like a base value with like the baud rate, 1900 baud, and no multibus cards and whatever stuff like that. And then it should write that into the clock chip. So on all subsequent reboots, it shouldn't give you a multibus error, but except it did on that first one because of the corrupt data. Well, in this case, it can't do that. It detects that the config value is invalid, but it can't write back to the chip because something's wrong with that part of the circuit, right? We've already determined that. And therefore, every time we power this thing on, it's gonna get a multibus error. So I have a feeling that if I fix the clock circuit, the multibus error will go away. Might happen one time, but on the subsequent reboots, it'll never come back. Of course, I have no battery in this machine, so powering it off might cause the multibus error to come back, and then you got to do one reboot cycle, and then it should go away again. Or I can install a battery so that once it sets up the config values, then it should go away. My presumption is inside the operating system, there's probably a command in there to configure the multibus cards, for instance. Like if you're adding like the 8-port serial card that's a multibus card to bring this up to 16 users, there's probably something to configure that. It writes into the NVRAM so that on subsequent boots, it's able to test that card, goes and checks what the contents of that NVRAM is. It says, oh, you have one of those serial boards. Cool, I'll do a little test on there. Good, passes, multibus good. Or there's a problem, multibus failure. So that's my logic and my reasoning for why we're getting 2 of these failures right now and why I think they'll both go away once I fix the clock calendar chip. Before I go back over there and start poking around the clock chip to see what activity we see on the pins, I'm just going to take a little bit of a tangent here. Remember, I think it was in part 2, I was trying to run some commands that I saw in the ROM code, and it looked like it was trying to load them off of tape, and it was of course not working because I don't have the tape. Well, what you see here on screen is that ROM code, and we have various things like format, MKFS, restore, file system check. When I typed all these commands, none of them actually worked. Well, over on Discord, a user, Transrail, found some old code here for an older version of one of these Plexus systems, but you can see here it has the Plexus boot ROM 1.0. And it seems that it's talking about using these commands. But the interesting thing is, these commands exist both on the hard drive and on the tape. And when you just type MKFS, it seems to try to load it off tape for default. But they're also on the hard drive, and I think they're on this hard drive too. So this stand directory, which I think stands for standalone, which means it doesn't require the rest of Unix to be running. I think we can run these from the boot ROM there in the colon prompt. So back on PuTTY here, the thing has failed. So again, we just push the exclamation point and that drops us to this colon prompt. Well, I don't want to run the MKFS command, that's make file system, right? But Transrail actually found a list from, I think, some source code for an old version of Unix. All of the commands that we can see in the ROM. I mean, pretty much everything that's in the ROM is here, except for, I don't think dconfig is actually there, but the rest of this stuff is. And this looks like it's actually using these commands here to move these onto tape, right? See, it says tape colon, and it's using dd in file out file over the tape. But some of these are gonna work. So one of them is stand/help. And I know I tried to run that in part 2 and it didn't work, but let's give that a try right here, stand/help. The hard drive is connected and spinning right now, by the way. And what's gonna happen? It's gonna hang. It's what's gonna happen. I see the hard drive LED blinking. Oh, that worked. That freaking worked. Look at this, display tape content. So yeah, this seems like this is a tape thing. These things are actually on the hard drive. They should be. Look at this. File 2, a copy of the Plexus System 5 Unix, the disk formatting and config program, disk as in hard disk or floppy disk, I don't know, it doesn't really say. Construct a file system, restore the file system, check the consistency, file system check. You can use dd to make copies of stuff. There's the file dump program, which I guess will list the contents of a file. Interesting. So we have du for disk usage, ls, and cat. Type return for more information about this item. Okay, just a few more files here. File 20, the minimum file system required to boot Plexus System 5. And file 21, a complete release of Plexus System 5 in CPIO format. All right. Right, so this tape contains the programs needed to bring up software on a new system or restore the system. So this is coming from the hard drive, but what's cool about this is it's possible we could reconstruct a tape image. I don't have a tape to put in the drive, but maybe with the Blue SCSI, we can emulate the tape drive and then we can recreate it and actually be able to start from scratch and have a larger hard drive partition, for instance. You know, if we use an emulated hard drive, I mean, there's all sorts of possibilities, right? Type 1 followed by carriage return to display the menu, or type 2 to display the tape contents. I think this is exactly what we've seen already. Oh, look at this. More information, this menu, display the tape contents, recreating the system software, standalone programs. I mean, let's look at 5 here. I wanna know if I could format a floppy disk. Formatting the disk, sparing tracks, initialize the disk is also used to configure your logical disk. Please consult your manual. Okay, I think this is for the hard drive. Let's look at number 8 though, disk format information for format. Oh look, different hard drives. What's kind of hilarious is it says 8-inch and 14-inch. The thing is, the hard drive that's in here is a 5 1/4 inch. So I have a feeling this stuff is like left over from the old versions. As far as I'm aware, the P25 and the P40, those like the big heavy duty Plexus systems that had a lot of cards in them and stuff like that, they used 8 and 14-inch hard drives. And it seems like when they ported that stuff over to this, they never fixed this. So yeah, clearly this is inaccurate information. So let's look at number 4 for standalone programs here. Certain standalone programs must be run before booting Unix. They perform a number of tasks necessary to allow Unix to run on a new system. Catastrophic system error results may require these programs to run. Okay, so like, you know, making new file systems or checking the file system, things like that. And definitely the way the disk partitions are set up on this thing, it doesn't really has a partition table, but the format is dev disk and then 0s1. So I think it's SCSI ID 0 and slice 1, slice 2, slice 3, things like that. When we actually booted up the system in part 3, the user partition was being mounted and the root partition was being mounted. And I think it was like slice 1 and slice 2 or something like that. And the next page here talks about the logical partitions or volumes on the first default disk. And then we have something called ISBC disks. Are these Intel Multibus drives? IS instead of DSK. And then PD is the IMSC drive, and then the DSLogic. I think people will probably know more about this than me, but I have a feeling this is probably all leftover stuff from the old systems as well that definitely had a whole bunch of cards in them for accessing disks in different ways. But look at this. Dev RFP 0M is the floppy drive, and then RPT 0M is the tape, and then you can do it with no rewind. All right. Okay, so what we know for sure is that I can run these commands directly off the disk, but they need to be in that stand directory, and I just don't know if like ls and cat and stuff is. They would be on the tape if we had that, but I don't think we do. So how do we exit out of this? I think we do -1. Okay, so let's try stand ls. Let's see if it's gonna give us a directory listing. Okay, well that's a bit odd. We got $2 signs and oh, it works. It freaking works. So we're able to see the hard drive, like the main drive here. Right. So I guess what happens if we run this again is it's actually asking me to add any kind of command line parameters. So if we want to look inside of a directory, because I do want to look in the stand directory here. So there it is. Those are all the commands that we can run right from this boot menu. So without even booting to OS, these are all available for us. Cat, whatever ccal is. Oh, that might have something to do with the calendar. Let's try that. Stand, oh no. The backspace key is misconfigured. It's not Control H, which it needs to be in here. Stand/ccal. I have a feeling this has to do with the clock calendar. That would make sense. I don't think it's going to tell us anything. I mean, the clock calendar is clearly not working, as the diagnostic test showed us. What the heck is this? System diagnostic configuration, Rev 1.0, diagnostic console. Oh, does this let us set a different serial port to be used as the diagnostic console? Baud rates? Oh, this is it. This is definitely how you configure the clock calendar, the defaults that are in there. It's like the CMOS setup for the system. Are we going to change the baud rates? No, we'll just leave those alone. And this is not going to work anyways. Memory size, 512K? No, it's 2.0. I don't know if we type 2.0 MB. Doesn't really matter, right? Because it's going to figure this out. Auto boot is set to no. Obviously, we have it set to yes. When you power up the machine, it's probably just going to do the /Unix and just boot right in automatically. Model P15. All right, maybe this is how you configure whether it's got the multibus or not. ICP, okay, so ICP is the Intelligent Communication Processor. That is what adds those extra serial ports. If the system thinks it's a P20 and it has the ICP installed, it's going to probably check those and result in the multibus error. This is all confirming exactly what I was thinking about. The clock calendar was causing the multibus error. All right, ACP is another communication processor. It's like asynchronous or something like that. I saw that in some document. Look at that, Ethernet. Does anyone have a multibus Ethernet card? Can we get this thing on the freaking internet? Oh, would that be cool or what? Clock speed? What? I'm pretty sure this thing runs at more than 10 megahertz. I think it runs at 12.5. Maybe this has something to do with the like timing loops or something like that. SCSI controller 0 in system. I mean, yes, right? It has a SCSI controller. SCSI 0, LUN 0. Is it hard drive, tape, or floppy, or none? Well, I know that the Omti 5200 that's in there, the hard drive is configured as LUN 0, the floppy drive is configured as LUN 1. So this is definitely HD. I mean, I'm typing this stuff, it doesn't really matter. Obviously, this is a floppy, and then none. For this, I guess you just go through them. Is SCSI controller 1 in the system? It's funny how it calls it a controller, but I guess it's talking about the actual drive. Yes, it is. Is SCSI 1 LUN 0 a hard drive, tape, or floppy? Well, I happen to know that is the tape drive. And we can just do none on these. And there's nothing else. So we have another SCSI controller in here. 2, 4. Oh, it's asking us all the IDs. I mean, I guess we could have multiple controllers. I could put more hard drives in this thing. SCSI ID 7, isn't that the actual main motherboard? But we'll just say no to that. Is all data correct? Yes. Update configuration? Yes. I mean, it's not going to work. The clock chip is bad, but it's so cool. We can configure the system right here in the boot menu before booting the OS. I just didn't know how that would work, and now we do. So let's do stand ls. And actually, what I wonder if I can just do that. No. Okay, stand ls. All right, I hear the hard drive doing stuff. It's funny how long it takes just to do a simple ls, but I guess because the OS is not running, maybe the ROM code is very slow and inefficient. But I know now I can type stand here, and there we go, we can see the other commands. Okay, so cat is obvious, ccal is obviously the configuration, core, maybe a core dump, disk usage, file backup, format, file system check. We already know the file system is good. File system DB, I don't know what that means. Help, ls, make file system, OD, which I think was the dump, and then restore. Let's just try stand OD, and let's see if that does anything. I'm assuming it's going to ask for something to dump, and I could try dumping the kernel, which I think is just /Unix. Yep, /Unix. Okay, there it is. Look at that. It's dumping the contents. Right. All right, that was a very fun diversion. Let me use my old screwdriver here, and I'm going to shut the system down because it's quite noisy. And the reason why I did that is because I think we need to do a little poking around to see how the circuit is designed that actually connects to the clock chip. Now, going back to part 4, I had mentioned that we were able to recover some data off the hard drive, and in that data was a net list and a parts list for this actual computer. Yeah, it's completely mind-boggling. Well, in the diagnostic process of trying to find the bad flip-flop that was causing the RAM not to work, I had to go through, and I have my papers over here, I did a whole bunch of like manual work, going back and forth and cross-referencing all these different files to figure out exactly what chips connect to what signals and how to like trace them through to figure out where the signals were going wrong. Well, it turns out the Discord channel has come through again, and there's now a utility to do it for me. I don't have to do it by hand anymore, and it's going to come in super handy because we're going to need to do the same work on this clock chip to try to figure out how it connects to everything. So what we have here is a Python script called netlist, and let's take a look at that real quick. And it I don't know, does a bunch of stuff. It's actually not very long of a program, but I'm not very good at Python. Whoops, I don't know how I was editing there, so we'll exit out of that. And what it's looking at is this cad.temp file. And I think this is like an amalgamation of the data that was recovered off the hard drive in a way that can be quickly parsed by this Python script. Well, I just took a look at the computer, and the clock chip is part number U2H. And all we have to do is run this command with the parameter of the chip that I'm trying to enumerate all the signals on. And we do that, and boom. All that work I was doing manually is now done in mere seconds, not even seconds, in a second. So that's the clock chip, MC1468818, 24-pin DIB. These are all the nets. Now, unfortunately, a lot of these nets, and that's just the way the files are, they're not really named anything. It's just net and then number as opposed to a name like ground or, M reset. But what this does, it shows each of the pins that is connected to something, and it shows which chip on which pin it goes to. Now for ground, for instance, it doesn't really show it, and that's because if you look at the net list under ground, it's like a zillion chips on there, so there's no point to look at that. So anytime there's a plus 5 volts or VCC or ground, it doesn't show it. Now this is a clock chip. It doesn't run on the normal 5-volt circuit, it runs on a BAT circuit, B-A-T-T. And that's because that's normally hooked up to the clock battery because this chip needs to stay energized while the system is off. Also, due to a little quirk in the way this thing runs, anytime there's a pin that's not connected to anything, instead of saying NC for no connection, it doesn't list it. So the reason why there's no pin 1 is because that chip must be just not connected to anything on this machine. Now, a feature I had asked to be added to this, and Peter, who created this, is working on it, is to enumerate if the pins are not connected, just like print that so we don't, miss that. But also to use commonly available databases that are existing out there to tell us if the signal is input, output, or both. And also if it's a standard chip like a 74LS00 to tell us what actually each pin is. So there are databases out there that have that information readily available. And for this clock chip, for instance, well, we don't really know what any of this stuff is here, not without looking up the data sheet. So that one may never actually be look-upable, but on a lot of other components, they are commonly available in databases, and it's just a handy time saver to not have to go look that stuff up manually. Either way, when we take a look at this, a few things we can ascertain right away. So M reset, I happen to know this is the reset signal that goes into that chip from the reset circuit. And where the power supply stopped working for reset, that is where I connected the ATtiny reset signal in. I actually soldered onto the chip right on the clock chip on pin 18 because I knew that was the input for the reset circuit. And I happen to have cut the trace on the back of the motherboard that goes to the power supply because the power supply circuit doesn't work. So I just cut that trace. So that signal is reset active low. And then the bat signal, we already know that that's the battery. And this signal right here, cal.ce, calendar chip enable, I'm assuming. And whenever it has a little dash after it, it's the older convention, but that means that that is an active low signal. On a more modern design, you might write a /cal.ce or cal.ce with a line over it. All of those things mean the same thing. It just means that that signal is active when it's low. If that signal doesn't go low, that means that chip is never going to communicate on the bus. And that goes the same for ROMs or anything else you're trying to troubleshoot when there's an enable problem. Now, when we take a look at these other pins here, 4, 5, 6, 7, this seems a lot like data lines or something like that. So let's just take a look at one of these other chips here. So all we have to do is just run this again with this other chip. Oh, this is an LS244. So yeah, this must be a data line. And in fact, what was the net? I don't know. The net we were on was like 734 or 732 or whatever. And 734, yeah, okay, so see this? So it has BA, DMA. So DMA is the processor that's running the diagnostics. BA is buffered address. That's what I'm assuming that is. And I happen to know this chip uses multiplexed addressing and data lines. So that means that the 8 lines both handle addressing and data. So if we do this other chip here, oh, there's a lot of stuff on here. This is going to be data. Yep, BD, DMA. So buffered data. DMA 7, 6, 5, 4, 3, 2, 1, et cetera, et cetera. But there is data line 0, so we have 7 all the way, 6, 5, 4, 3, 2, 1, 0. Yep, okay. So we know for sure, going back without even checking the data sheet, that almost certainly these signals right here are going to be all the data and address lines. So we know for sure if one of these chips, this LS244 or the LS245, aren't being selected correctly, then the clock chip will never be able to talk on the data bus. I think let's not get ahead of ourselves. First thing you always need to check if you're trying to figure out why something's not communicating on the bus, a chip that is always a chip enable line. So let's take a look at pin 13. I'll get the oscilloscope hooked up. The scope probe goes to the Zoe ZT703S, whatever this thing is. A few people have asked me about this, like, oh, what am I doing using this thing? I bought one of these on a whim. This thing is cheap. It was like 70 bucks shipped. It's a decent oscilloscope. It's actually not bad. I don't love it, but I don't hate it either. And I like the form factor, and it's an okay multimeter. And after some firmware updates this thing has gotten, this is actually not a terrible device. Now, the reason why I did not review this is there are so many other reviews of this. And by the time I got it, like 50 other channels had already done it. And I thought, what's the point? But if people want to see me review this, then I can. But ultimately, it's a decent device. If you need a cheap $70 oscilloscope and multimeter, it's not bad. USB-C updates and charging, and the screen is big, it's quite visible, and the update rates are decent. The UI is frustrating at times, but not that bad. I like it. It's not as good an oscilloscope as the Handtech portable scope I have, but the UI is better on this, and the screen is better. And my eyes aren't that good anymore. Anyhow, it's hooked up to the chip here, and when I power this on, the chip select line on here needs to be at 0 volts or around there when the chip is being accessed, at the minimum. So let's turn this on. I have the little plastic tool I'm going to use. Okay, it went up to 5 volts, so that's okay. It's like it only needs to go low while the chip is being accessed. If it's not being accessed, it's fine. It's up at 5 volts. Now over on the screen over there, I can see the diagnostics running. It just says self-test 3.3, and we'll keep an eye on this right here and see if it goes low. And nope, over on the console, I can see that we have the self-test failure now for the multibus and the clock, and this never budged at all. Now, even though the update rate seems a little bit slow right now, I happen to know while this is triggered, it actually does update much more quickly. So if we had a pulse where it went low, we would have seen that. It would show up on this thing. That's one thing I don't like about it, is I don't like how the update rate is so slow on this when it's just sitting here not triggered. It's just in the run position. But anyways, it would have shown something and we got nothing. And that means without a doubt, there is no way, let's turn this off because it is so noisy. There's no way that that clock chip can work if it's not selected. So I need to go back to the computer over there and let's figure out exactly what that thing is connected to and see what selects it, and then we'll fix it. All right, so back with the Python script, we're looking for this line here. It's going to two things, a resistor and a transistor. Let's start with R47 and let's see what that goes to. So R47 is on the Cal CE. Okay, that goes to the bat signal, battery. I happen to know because I looked at this when I was putting on the little AT Tiny. The bat signal is just the 5-volt rail through a diode because, of course, it needs to either charge the battery with 5 volts or it needs to power up the clock chip with 5 volts, or not 5 volts, whatever the original battery was, probably like 3.6 or something like that. So if we take a look here, designator bat not found. Did I type it wrong? I don't know, BATT. Well, okay. Well, anyways, it's right there and it's enumerating it. It goes to various things. So we know there's CR1, that's the diode that then goes to the 5-volt rail. In fact, I think if we do this with CR1, we'll see it's going to VCC. Yes, there it is, VCC and BAT. So that's, there's a little bit of a voltage drop through there. So the VCC becomes, you know, whatever, 0.6 volts less. But that does work because when I was probing around to install the AT Tiny, I almost connected to this bat signal, which would have kept the AT Tiny running all the time, which it wasn't necessary. And I decided to go not onto the clock chip, I actually took 5 volts off a chip that was right below it. I'll write down the signals we need to check. We need to just make sure that bat does have that 4 point whatever volts on it, because the clock chip isn't going to work without it, but it looks like the chip select circuit obviously is connected to it as well, so we just need to make sure that that looks good. All right, the other component was Q2, so we have a transistor there. So let's take a look at that. All right, there it is. It's connected to ground. It's connected to the chip select line, and it's connected to 2 other resistors. So R51, let's see what that is. Okay, that seems to go to the reset signal. That goes to my AT Tiny. All right, and the reset signal goes off to various things. That is fine. And then what's R52? R52, that just simply goes to ground. So one of the things we can tell for sure here is that none of these nets connect to logic chips, none of them at all. Well, the only one that was connected to anything was this M reset. But we know that the chip needs to be enabled when the computer is not in reset. So I assume it's connected to that, something to do with it, like, I don't know, maybe it's a power saving thing or something like that. I'm going to think about this a little bit, but yeah, it's definitely not what I expected, because I would expect it to be coming from a logic chip. So anytime the CPU tried to talk to the click chip, it would be chip selected. Otherwise, you know, it would be idle. But I guess that's not the case. And actually, if we think about it for a second, remember that the data and address lines for the clock chip are connected through buffers, LS244s and 245s. That means that you could actually keep the clock chip selected all the time, and that wouldn't have any negative effect on the rest of the system, because obviously there's logic that activates this LS244 or the LS245 to connect the data or the address line to the clock chip. So maybe the clock chip is just enabled all the time, something like that. I don't know. Let me go have a think on this. All right, well, I was over on Discord chatting with Super SVGA, who helped me before with a bunch of stuff in the previous parts, and Super SVGA came up with this simulation of the circuit, and we took the values of the resistors that I actually saw on the board, because they actually were different. Even though it said 10K, if we looked at the parts list here, wherever it was down here, yeah, 10K and 10K, I looked at the board and it actually had 520 ohm resistors here and here. It looked like what this circuit is doing, and Super SVGA kind of talked me through it a little bit. It looks like, as I thought, the clock chip is either selected all the time while the system is running, or it's not selected when the system is off. And this is probably some kind of a power saving strategy. When the system is running on battery, probably the clock chip shouldn't be selected. And if you look at this circuit, let's just talk through a little bit. So here's the 5-volt battery signal, right? And right now, the transistor is not turned on. If this transistor turns on, what happens is this line through this resistor gets connected to ground and actually will pull the Cal CE or the chip select line down to 5 volts. Right now, you can see right down below, I can't point at it because if I move my mouse, or no, if I move my mouse, it goes off of it. The voltage of this signal is 5 volts. And that is when the reset line is not at 5 volts. So while the system is in reset, which means the reset line is down around 0 volts, or the system is just off altogether, which means the reset line is down around 0 volts, then the battery signal is just routed directly to the Cal CE line through a 520 ohm resistor. When the system comes out of reset, which means that the AT-Tiny pulls the reset line up to 5 volts, then you can see we have electrons flowing through here, and the Cal CE line now becomes 68 millivolts. So that is equivalent of a low signal, which enables the chip select line on the clock chip. Clearly, the circuit is not working properly. When I power on the computer, the system is actually in reset for a couple seconds. That's what the AT-Tiny does. So this Cal CE line should be at 5 volts initially for a couple seconds and then drop down to 0 volts. Well, it never drops, right? And when the AT-Tiny takes the system out of reset, 5 volts is available on R51 here, and that should bring this down around 5 volts, and that's just not happening. Now, when it comes to failed components, obviously if this resistor were missing, well, that's always going to be up there at 5 volts no matter what. And if this resistor was missing, now according to the simulation, even with that resistor open, it still works as desired. At 5 volts, the chip would be enabled, so it's not that resistor. And I don't think it's this resistor because they would be at 0 volts all the time. So the only possible candidates really are this resistor here, this 2K R51, or the transistor being bad, or the clock chip, I suppose. The clock chip signal could be bad internally, and it's forcing this transistor up to 5 volts. Although, if that were the case, that would be shorting through the transistor to ground, and the transistor would have got hot and died already. So I think I need to go over there and check a few things. I need to check that the base on the transistor is 650 millivolts or whatever it says there. I need to check that the emitter is actually connected to ground, because if it wasn't, if we take away this ground, then it's always going to be stuck at 5 volts. So I need to check that it's actually grounded. And I guess, I think that's it. I don't know what other things could cause this to go wrong. So yeah, I need to check that resistor. Well, I don't even need to check that resistor because this is a voltage divider right here. All I need to do is just check the voltage on the base to make sure that that's there, and just make sure that the emitter is actually connected. And I suppose I'll check to make sure the collector is also connected to here, because if this were somehow broken, like a trace was broken here, and this resistor just went right to Cal CE, and the transistor wasn't actually connected, then that would mean that it would also be held at 5 volts all the time. Okay, I know what to do. I'm gonna go do that right now. All right, I am back, and well, I don't really see anything wrong actually. So the base is around 650 millivolts. That's what I saw on the multimeter. And then the collector was connected to the chip itself. I actually have full continuity between there. And the emitter is definitely connected to ground. So that really just leaves the transistor as the only bad part that could be bad here. Now this whole circuit seems to be something to do with power saving, as I said. And one easy way to test without even taking this out is I'm just gonna ground the collector here, or just ground the Cal CE line altogether. That shouldn't cause a problem. It's not gonna cause a short because this resistor is here, 520 ohms. It's gonna waste a little bit of current, but it's no big deal. This is just a test. If this does work, then I'll just fix the circuit. I'll take the board out though and desolder it. So let's go do that right now. So what I've done is I clipped onto the chip select line and I hooked up a 100 ohm resistor, and that goes to ground. And this thing should be constantly enabled now. So with the oscilloscope hooked up, let's power on the machine. And yep, indeed, it's down at ground now. So this is working perfectly. All right, well, the system booted, and that's it. That's the boot we just had. And yet it's still telling us that we have a clock failure in the same error as well. So let's go in here and let's run that clock test. Now I think, by the way, I can run that test. Yeah, the H command lets me run it independently. Run clock A, TA, I think is what I type. No, we are still having issues. I've been poking around the clock chip. I don't see anything wrong. All the various signals, like there's a address strobe and a data strobe signal, those are good. Read write looks good as well. In fact, when I run the diagnostics, the TA, where it lists all the memory addresses, it's getting wrong. I can see it pulsing. Everything looks like it's working. Now the question is, why do we not have a working clock calendar? My feeling is that I must have somehow damaged that clock chip when I was installing the AT-Tiny. I guess. I don't know what else it could be. Although in part 4, when I was using the Arduino to boot this thing, I hadn't yet soldered anything onto the clock chip, which is where the AT-Tiny is. And I just don't remember if I actually got the system booted or not. I'm gonna have to go review my footage to see if I ever let the thing finish all its diagnostics and try to boot the system. Maybe I did, maybe I didn't. Well, you know, to be honest, now that I think about it, I guess it's kind of irrelevant. The system's not working right now, even though it looks like it should. So I think what I need to do is I'm gonna socket the clock chip. And that will allow me to swap a different one in there. I'll just take the ATtiny off. I have extras of those chips. I'll swap a different one in. I could even use a Dallas chip in this thing, and that should work. So I'm gonna go do that right now. Okay, we're ready for a test. This is the chip that was in there. I've removed it, and I have a bunch of chips here, spares, Dallas, but other 146818s that are compatible. So there's a Hitachi part in the socket there now. I have the ATtiny removed right now, so I'm gonna have to manually bring the computer out of reset. All right, here we go, powering up. Computer's in reset, as it should be, and we'll bring it out of reset now. Here we go. Oh, one other thing, for that whole circuit with the transistor, I decided to remove one of the resistors, R51, which if we take a look at the list here, that says it was a 10K, oh, it was this one here, but it was actually like a 510 ohm resistor. So I removed that, and that actually renders the whole transistor circuit inoperative. So I just put a little jumper link on the back side of the board to bypass the transistor entirely. Look, look, the clock has not failed. So we're just getting a multibus failure, which is exactly what I would expect to happen. Let me grab the keyboard here. My hypothesis is if I reset the computer, we will not get that error anymore. But let's go into the DMA mode here and let's do TA. This is a clock test. Passed. Freaking passed. And T9 is the multibus test specifically. That's gonna pass. Right. Right, okay. So wait, this chip was bad? I mean, it was working. I mean, it was close to the battery, but it didn't look crusty. But I did solder onto the legs, so maybe I damaged it by doing that, I guess. I don't know. Okay, so to test my hypothesis about the multibus failure, I'm going to disconnect the resistor, which is gonna put the computer in reset, reconnect it, and we're gonna reboot. And if my hunch is correct, we're not gonna get the multibus failure anymore. So the computer's in reset, and now it's out of reset. Now, if we do get a multibus failure, it's not that big a deal because we know how to run the clock calendar setup utility now. And I'm just thinking here. So I think what I'm gonna do is I think I'm gonna install one of these Dallas chips. I just have to do the little Dremel trick to put a new battery on it because these are all dead. I have, how many do I have? I have 3 of them here, the kind that will work in this machine. Oh, we still got the multibus failure. Interesting. Okay, well, I have the hard drive stuff disconnected now. I'm gonna power the machine down, reconnect the hard drive and the SCSI, and let's see if I run that setup utility, if that fixes this problem. All right, drive is reconnected to power, SCSI is reconnected. Let's power the machine up. And I'm gonna clip the resistor on to bring it out of reset. There we go. I can hear the drive spinning up. All right, multibus failure. Yes, we know. Wow, clock chip died as well. I'm still a bit flabbergasted about that. Okay, diagnostic console, change the baud rates. I'm just gonna leave that as is. We have 2.0 megabytes. Auto boot, no. Let's put it to P20 since that's what this is, but we do not have the ICP or the ACP or Ethernet. Clock speed should be 12.5 as far as I'm aware. SCSI controller 0 is in the system, yes. It's a hard drive. Then we have a floppy. Then we have nothing. SCSI controller 1 is the tape drive, so that's TP. I mean, it doesn't really matter, does it? These other LUNs aren't used, and these other SCSI controllers are not used. Where's 3? It's funny how it skips over 3. All data correct? I'm gonna say yes. Let's update the clock calendar. Okay, let me reboot it again by taking the resistor off. All right, system is booting back up. If all goes well, we won't get that multibus error anymore. I'm keeping my fingers crossed that that's the case. It's just corrupt data. Oh, incidentally, when I was poking around on the bad clock chip and I had the oscilloscope connected, without a doubt, I could see the clock chip being accessed early on in the boot process. When you first power on the machine, this chip is read a bunch of times, and that's even before it gets to the clock test. So that means it is reading configuration stuff. Oh, clock failed again. No, no, no. Is that error different? A007. Oh, you gotta be kidding me. What's happening here? Okay, before I jump to conclusions, I'm not gonna worry because the way I was doing the reset with the clip leads. It's not ideal. I think ultimately glitching the reset line is probably not a good idea, you know, using the clip lead. That's going to cause all sorts of weird issues. And okay, yeah, we lost the config info. Okay, whatever. Let's boot the system completely. So I hit exclamation point, and I'm just going to push enter, and hopefully the system boots. Hard drive light is blinky blinky, and let's see if it boots. Before it was freezing, right? After it would show the free memory, I think because the clock chip wasn't working. So fingers crossed, this actually works. Oh yeah, that was it. It's working now. So the bad clock chip keeps the system from booting. Oh, look at that. So it remembers the last time the system booted, and that's the time I typed in. And remember the first time we booted the system in part 3, it was 1989. So that confirms that was the last time this system was working. Is the date correct? I'm just going to say yes, just to skip over this. Do you want to check the file system? I think we're going to say yes, because the system did crash, and I'll let this run through the check. It was crashing in part 3 when it was getting those errors, right? I feel a big sense of relief here, though, that, yeah, the clock chip went bad, and that caused this thing not to work. So I think what I'm going to do is take this Dallas chip here. I'm going to put the 2032 mod on it, use a Dremel to kind of eat away at the case a little bit. And then I will stick this in there, and this should work in place of that. And then we should have a clock calendar that actually is able to save the settings. But the system is booting up here, which is excellent. There we go, we're ready for login root. And there happens to be no root password on here. We did learn that. And there we go, we're freaking logged in. Now I'm curious if there's a reboot command, so I should be able to run that ccal command right here as well. Yeah, oh, core dubbed, okay. You cannot run that command while you're in the operating system. I guess these stand commands do not work while the OS is running. They do not. And what I'm going to do now is modify the Dallas chip, and I will reinstall the ATtiny so we have a proper working reset circuit. And hopefully after that, the system is fully operational. Okay, the motherboard has been modified. I actually put the ATtiny on the back side, and I have my Dallas chip all modified here with a CR2032. The one thing I forgot to mention is the original Motorola chip that I took off the board actually has an auto detection between Intel and Motorola mode, but all the later versions of that chip don't have that. So for the Dallas chip to work, you actually have to put a 10K or a 4.7K between VCC and the Sense pin, which is pin 1. It's a Motorola/Intel mode change pin. So to use this Dallas chip though, I do need to hook that pin up to something, and I hooked it up with a resistor on the back side of the board as well. This is exactly the same thing I had to do on my BBC Master 128 when I installed the replacement clock chip, because I think it also used the same exact Motorola chip in there originally, and I put the Necroware replacement chip in there instead of one of these Dallas chips. And that one also required pin 1 be pulled up to 5 volts, otherwise it wouldn't work quite right. So I'm going to stick the Dallas chip in here with the battery, and let's see what happens. And I'm ready to steal this thing, turn it on with a screwdriver. Here we go. And I won't need to do the reset thing anymore. Should come out of reset. There it is, it came out of reset on its own. Now incidentally, when I had the Hitachi chip in there, that was the replacement chip that I put in instead of the Motorola chip. I think it also needed that resistor on the backside. Probably explains why it wasn't quite working with the Multibus. We were still getting that error. I think it was because of that. Although, I guess we're gonna find out shortly if that was actually the case. Tape drive making all sorts of noise. Okay, Multibus failed. As long as we don't get to clock failure. No clock failure, that's good. All right, config invalid, totally understandable. So what we're gonna do is we're gonna run that stand cc config program, not cc config, ccal. This will run off the SCSI drive. All right, diagnostic console, baud rates, nope. Memory size 2.0 megabyte, auto boot, nope. I'm just gonna leave this as P15 for now, just so it doesn't even do a multibus test anymore. Definitely SCSI controller, hard drive, floppy, and the rest is nothing. And I'm actually gonna say no for the tape drive, because I actually don't know if the tape drive is ID 1 or not. So we'll just skip past all this stuff here. All data correct? Yes. Update configuration? Yes. I'm gonna do the old reset here with the screwdriver, and let's see what happens. Okay, there we go. System is rebooting. So theoretically, we should not get the multibus error, hopefully. And before, when I didn't have the resistor installed, when we did this, I got that proc error and a clock error. And I think that was because the resistor was missing. Let's see what happens. I kind of remember on the BBC Master, when I didn't have the resistor in place, there was a bunch of garbage that came back from the clock chip when you didn't have the resistor in place. So let's see what happens. I think we're golden, everyone. I think we're freaking golden. Because it's doing the parity check right now. Oh no, proc failed. Interesting. Procs mean, I wonder. So we didn't get the clock failure. We didn't get the multibus failure. Well, we can run that utility again. Stand ccal. Oops, that's not it. Stand ccal. But look, it definitely retained settings. 2 megabytes. Auto boot, no. So let's do P20. You know what? Before I press enter here, I'm going to hook the oscilloscope up to the clock pin on the 6810. I've never done that. So let's see what it actually is running at. All right, yeah, it's running at exactly 10 megahertz. At least, well, at least the processor I probed there. So we'll just leave that as 10 megahertz. And we'll just go through these. I'll just hit enter since it seemed to have retained everything. All data correct? Yes. Update information? Yes, we will. I'll reset the computer again. There we go. So interesting is the multibus error, it went away, but then we got the procs error. What does that mean? What is procs? So while we wait, it's kind of cool that the Dallas chip seems to be working. Definitely saved the settings, and the battery on there should keep it going for, you know, years and years and years. It's a very efficient chip. The Motorola needed that giant NiCad battery to retain the settings for any reasonable length of time, but the one that the Dallas has, there's that proc error again. I guess I should power the machine off and back on and see if that goes away. I'll just let the machine cool down for a moment. I guess this is the real test as well. Is the battery working? I used a little mini Dremel here to cut away at the side of it, and then my little engraver tool to cut through the pin. I like to personally cut the battery off that's internal, that's epoxied in there. I like to cut the little metal part that goes from the chip to that battery. That way, the battery I put on there, the CR2032, is not trying to like back charge the little whatever coin cell that's inside of there. Okay, come on. No procs error. No freaking procs error. Nah, proc fail. Let's go in here and let's run the tests again. I think I just hit T. This will run the entire gamut of diagnostics here. The funny thing about that proc error is when the system booted up before, like when the clock was corrupted, we didn't get it, and now we are. So it feels like it's something to do with the config settings that I set up there, because the error appeared after I set up the clock calendar with that utility. Okay, wait, look at this. Procs. SC7 not expected, failed. SC7? Ah, is that SCSI? SCSI controller 7, and I hit no. Let's fix that. I'm gonna reboot the system, and I'm gonna put yes on 7 and see if that does anything. All right, hit yes. And it's asking what it is. I don't know what it is. I don't know, I'm just gonna put HD. I don't know what else to put there. And we'll say yes, update config, sure. And I've escaped right to the DMA menu here. And I think if we do H, we can just run that particular test, TF. No, same thing. Oh, different error code though, look at that. F022. And before we were getting F035. Now I notice if I hit Q, aha, look at this. System configuration, SC0, SC7. Is the tape drive SC7? I mean, the tape drive is a separate SCSI device. It's not part of the interposer, which is definitely ID0. So SC7, it's gotta be the tape drive. Okay, I'm gonna put yes, and we're gonna do tape, TP. And there's nothing else on that one. Is this correct? Yes, it is. Update config, yes. Reboot the machine over there. And let's see if this does the trick. It's quite the learning experience. It was interesting to learn that in the DMA menu, Q gives us the system configuration. And normally when the diagnostics pass, we will see this exact message. I think it just kind of tells you like what it's found. And let's see if that does the trick. You know what the fact is, how it skipped SCSI ID 3? I think that kind of tells us that the computer itself is SCSI ID 3. That's unusual. I don't think I've run across that in my entire career. Oh yes, that was it. That was freaking it. This thing is working now. Hit enter and we're gonna boot into Unix. Quite the learning experience, but you know what? The clock is good. I can turn this off and tomorrow it will freaking remember all its settings because that battery is on there. That is awesome. We ended up in single user mode, so I think we could do that. And this should put us, yeah, it should continue. Oh, look at the time. Oh, it's because it's corrupted and it's reading it back from the actual clock. Let's check the file systems one more time. This thing is working. Question is it gonna stay working? Or is it gonna fail in some other spectacular way? I don't know. All right, there we are. It's logged in. It freaking is working again. Oh, that is just so great. What I should do is try to do a shutdown here. Shutdown program. System being shut down right now. So that was a broadcast to all other users on the system. I'm gonna turn this off tonight. I'm gonna go to bed. And then we will see in the morning if this thing boots up properly without any errors. I really hope this thing works. I'll see you in the morning. It's been a couple days since I took out the bad clock chip. The Dallas has been in there with the battery the whole time, and I think it's now time to test this thing. Did the Dallas clock chip retain all my settings? And will we actually get a boot with absolutely zero errors? Guess we're gonna have to find out. I have a lot of confidence that this is gonna work, so I'm gonna reinstall the Multibus card cage plus the resistor board and put the cover back on this thing because I want this thing to have good ventilation. And if it does work, I wanna let it run for a while, kind of stress test it, let the air circulate inside here and just make sure this thing is actually stable. I only got about 30 minutes or 20 minutes out of it the first time this booted up and worked. So hopefully we can break that record and maybe get a few hours out of this thing. And the Plexus is all back together. The one thing I ran into is that Dallas clock chip sticks out a little far and it actually caught the lip of the case as I was sliding it on and it knocked it out of the socket. It actually clears the side of the case without an issue and it even clears the lip. You just have to make sure when you slide this on you don't sort of tilt it one direction, which just makes it a little too close. I'll have to put a note on the back that says when removing case, be cautious of the battery on this side, just to remind myself not to knock that out next time. All right, let's power up the beast. Here we go. All right, we don't see the Plexus banner because I had to restart PuTTY when I first turned this on. I always forget that when my lab machine goes to sleep, for whatever reason, PuTTY loses connection with the COM port. Hopefully it is actually working. And one thing you can tell is, oh wait, look, yes, it's freaking working. All right, so auto boot is turned off. All I have to do here is hit enter. By the way, system 5.2RA, what does that mean? I don't know. There we go, yep, run level 2 automatically. Is the time correct? June 4th? Yeah, that's it, 1:31. That is literally what time it is right now. Ignore the year being wrong. That's a problem with the clock set utility. Time is correct. Let's check the file systems again. I mean, we don't really need to, but may as well. This thing is actually freaking working. Wow. There we go, I just broadcast it freaking works to all the other users on the machine, which is no one right now. This thing is actually fixed. At least it's fixed for now. Part of me can't really believe that this computer is actually working. So I think what I'm gonna do now is just let this thing sit here, boot it up into Unix for a while, and make sure that it doesn't fail. I want it to at least run for, let's just say 3 hours. I'm just gonna pick that amount of time arbitrarily, and hopefully it stays working. And then we can consider this thing fixed, at least fixed for now. And it's been a few hours since I powered this up and the Plexus P20 has been working perfectly. Well, not quite perfectly. I think I figured out there's something going on with the floppy drive on here. I don't think the spindle is spinning, and anytime you try to access the floppy drive, what happens is the interposer gets confused and the floppy LED stays on and then the hard drive is no longer accessible. So it actually crashes the system. Well, it doesn't crash, it just halts the whole system. Because even if you try to go to a second serial port and log into another console, it can't do it because the hard drive is inaccessible. It's probably one of the negatives of using an interposer that handles the floppy drive and the hard drive at the same time. I think what's going on is because the drive's not spinning, there's no index pulse going to the interposer. That must confuse it. So when it comes to future plans for this machine, now that it's working, there's still lots I want to do. First off, we have to finish sanitizing the hard drive image that we've created of this thing. That way I can upload that to GitHub so people can take a look at it. I've had a lot of requests for getting access to the hard drive image. So hopefully by the time this video is out, I will have already been able to do that and it will be uploaded, and I'll link below in the description to that image. I also obviously need to fix the floppy drive because that's not working. So take that out, see if I can get that working. I'll do it externally on a PC. Also, I want to get the BlueSCSI working with this machine. I talked to Eric, who's one of the lead maintainers for the BlueSCSI project, and he gave me some tips and pointers on configuration options to use because this thing obviously is expecting the Omti 5200 in there for the hard drive to work. So in a future video, I'm going to try that out because I need to let Eric know if there's any fixes that need to be made to the source for the BlueSCSI to add this weird, rare computer to the compatibility list. I'd also like to try to figure out how to get files on and off this computer. The floppy drive, obviously, if that were working, would be one possible way, or potentially copying Kermit source code or Z-modem source code and then transferring files over the serial port. But right now this seems to have a UUCP mechanism for transferring mail between various systems over the serial ports. But I think I'd like to get something a little bit more direct, like the floppy drive or some other way to get stuff on and off of this. If the BlueSCSI works, I can obviously take the SD card out and put that in a modern computer, and then hopefully we can figure out how to mount those images on something modern to copy files on and off this as well. Anyhow, as you can see, there's still lots more to do with this machine. I might need to take a little bit of a break though and work on some other stuff for a while. It's been sucking up all my time, this beast, but I do like it and I'm really excited that the thing is working, and I'm definitely going to do some more stress testing of this thing and let it run for even longer than just a few hours, just to make sure that nothing else is ready to break on this thing. But so far so good, 100% stable. And the last thing I want to add is I do apologize. This video I know is a little bit all over the place, especially while I was working on the clock circuit. I edited some of the video already before I've done this outro, and I noticed, I don't know, it's not up to my usual standards. So hopefully you liked it. If you did, thumbs up. If you didn't, you know what to do. A huge thanks again to everyone over on Discord who has been helping me with this thing. I really don't think I would have been able to get this working, or it would have taken me way longer if it wasn't for the help that everyone over there has been giving me. And also a huge thanks to the folks who were helping me with the disk image and recovering the data off this thing, because obviously that hidden data that was on that lost partition was the other part of this machine that was absolutely essential for getting it working. So that's going to be it. Huge thanks to my patrons. Names are going up the side of the screen. They get early access to videos. They make it possible to do this full time. So yeah, big thanks to them. Thumbs up, subscribe, usual YouTube junk. And that's going to be that. So stay healthy, stay safe, and I'll see you next time. Bye-bye.